So thank you, Paul, for a very kind, yet overly long introduction. And now I am intimidated because I could never describe the research as well as you've just done. So perhaps we should conclude the lecture at this point. I'm sure if I would ask anyone who has not used a cell phone, computer, or accessed the internet in the last 24 hours to raise their hand, would see no hands going up. Information technology actually is critically important. And in fact, not only is it economically important, it also can be very intimidating at times. And as Paul has already noted, it's been widely recognized that chip-scale integration is going to be the next great technological leap that impacts the world. And it will revolutionize information technology, all aspects. And as Paul has already covered this first slide, I'll just move on to the first topic I'd like to introduce you to, and that is that we're readdressing two grand challenges widely recognized by federal agencies, the National Academy of Science, by professional societies, and by large companies such as Lockheed Martin and IBM. And the first of these grand challenge research pursuits is multiscale theory for theory-guided design and development of soft matter or complex macromolecular materials for transformative or disruptive physical and chemical properties. And the second grand challenge Paul has already alluded to is chip-scale integration of electronics, photonics, and plasmonics through development of sub-wavelength nanoscopic photonic circuitry and devices for next-generation telecommunications, computing, transportation, medical, and sensor technology. This includes both wireless technologies and fiber technologies, and a lot of devices for doing an enormous array of processing operations in the information technology world. I would remind you, when you think about generating, transporting, storing energy, there are three types of fundamental particles that you can think about. Electrons, which I'm sure you're all familiar with, photons, which I hope you're all familiar with, and also plasma and polaritons, which are hybrid particles intermediate between photons and electrons. And the next a great advance in information technology, I think, is well recognized to involve utilizing the best properties of each of these fundamental particles. If you're an engineer or a corporate executive, you look at technology drivers for this integration, and they include size, weight, and power, which is sort of obvious, but performance is also very important, both bandwidth, drive voltage, which also relates to energy or power efficiency, and from an industrial standpoint, manufacturing yield, in-field reliability, and cost are very important drivers. And in fact, chip-scale integration of electronics, perhaps the greatest utility of this, has been producing devices that are incredibly reliable, that can simply be tested, that avoid all the defects associated with human labor, and facilitate rapid and reliable testing or quality control. The economic drivers of photonic electronic integration, including chip-scale integration, are basically computer, telecommunications, sensing and imaging, and entertainment. And this upper slide, the technology driver, is illustrated by this graph that was provided to me by IBM at the outset of our STC, which was the IBM decision chart for whether you transmitted information using photons or electrons. And the interesting thing, by the year 2000, as a function of considering all of these parameters, the decision favored the use of photons, even down to chip-scale dimensions. The economic drivers sort of represent the smart card, which you can think of as being the next generation beyond the iPhone. Not only do you have GPS and your computer telecommunication capabilities, but you have many other features, including such items as laboratory and chip diagnostics, remote managing of your home, car, business, financial affairs, etc. I'd like to turn our attention to acknowledgements because, as Paul noted, this isn't my effort. The effort of many people who've accomplished amazing things. If I actually acknowledge all the people that I should be acknowledging, it would require about 4 slides and much finer print. So I focus only on people that have participated very recently in research here at UW and who have made a major contributions. Alvin was the executive director of our Science and Technology Center, and Alvin is the individual responsible for the first successful commercialization of organic electro-optic technology. Bruce Robinson was the leader of the theory thrust of the STC. Phil Reed was the director of the STC through the latter half of the center. Alex Jen was director of the electro-optic and all-optical signal processing thrust. And students, such as noted here, made major contributions, including those students from chemistry denoted in blue and my students from electrical engineering denoted in orange. And of course, many faculty members at other universities, both internationally, such as the Karlsruhe Institute of Technology and the ETH in Zurich, but also nationally at USC, UCLA, Caltech, contributed to particularly the development of device and systems application. This is the last group picture that, from my group and that of Bruce Robinson. This is 2 of my students, including Stephanie Benet at the Landau meeting of Nobel laureates. And of course, this is Bruce Robinson and Alvin Querim killing a salmon. I'd like to illustrate a couple of very basic ideas. An electro-optic starts with a molecule. And basically, it's a dipolar molecule that consists of an electron-rich donor region, an electron-deficient acceptor region connected by pi electron conjugation. If you apply an electric field to that molecule, you perturb that electron distribution, such as shown in this cartoon. And if light interacts with that molecule, it will be influenced by that perturbed charge distribution. For example, if you push electrons across, as shown here, you increase the dipole moment of the material, and light can interact, the electric field of light can interact with that charge, perturbed charge distribution, for example, retarding the velocity of light or changing its phase. And we would note that what we have here is a situation of interacting of 3 types of electrical phenomena. One, the perturbed charge distribution, which is not symmetrical. It's going to be axially symmetrical for a molecule such as this, or approximately. It'd actually be a tensor because we won't have perfect axial symmetry. And then you have the electric fields of low-frequency radiation, such as DC to terahertz, and the electric field of light. So you're going to need 3 types of cosine functions to describe the optimum effect. In short, you're going to want to get a large macroscopic effect, you're going to want all these chromophores lined up in the same direction and in the direction of the electrical and optical field vectors. And if you, for example, take these materials and you induce alignment by electric field pulling, you apply an electric field to the material when it's near its glass transition temperature, you can align chromophores in one arm of this device called a Mach-Zehnder interferometer in this direction, you can apply a pulling field in the voltage in the opposite direction to align molecules here. When an electrical signal comes in, if the magnitude is such to produce a forward phase shift of 90 degrees in this arm and a retarding phase shift of 90 degrees in this arm, the two optical signals will be 180 degrees out of phase and light will be turned off. So what happens is that you transduce this electrical signal onto this optical transmission as an amplitude modulation. So we've introduced you to the fundamental ideas at the molecular and materials level and at the device level for electro-optic activity. And to continue, we're going to need to introduce some terminology to you. So we need to introduce you to the measure of electro-optic activity, which is this principal element of the molecular hyperpolarizability, which describes the interaction of these two fields with the perturbed charge distribution of the material. And that can also be considered the figure of merit of an electro-optic material. And it is related to two important parameters. In the independent particle limit, it's going to relate to the ease at which an electric field perturbs the charge distribution of a molecule. That's called the first molecular hyperpolarizability, denoted by the symbol beta. The second factor relates to the product of the number density and the order parameter. We have a cosine cube function because three types of tensors or vectors are involved. And of course, if these are non-interacting, truly non-interacting particles, this cosine cube function would be independent of number density, and the electro-optic activity would just be the product of these. Since we're using a Pauling field to induce our acentric order here, in the absence of interaction between particles, that order parameter, called the acentric order parameter, would simply be related to the product of the dipole moment of the chromophore times the strength of the Pauling field. Now, if we look at this curve, it shows, and of course, then electro-optic activity should relate to the product of dipole moment times the molecular first hyperpolarizability. If we look at the evolution of experimental molecular hyperpolarizability as a function of preparing different molecules that define the state of the art in various years, we note that we achieved this rather dramatic improvement of molecular of mu beta as a function of using better acceptors and longer chromophores. Now, unfortunately, this curve leveled off at this point in time. And if we had truly independent particles, this measured electro-optic activity, R33, should track exactly this curve. But you see it doesn't. And the reason fundamentally it doesn't track is because of intermolecular interactions. So the particles are not truly independent. They're independent in the sense that we don't have direct pi-pi interactions between the chromophores, but we can have long-range dipolar interactions. And this accounts for the delay, and one of the triumphs that was affected by Bruce Robinson and his students and by my students was that of developing a theoretical understanding for understanding why we got this effect even for chromophores that were relatively dilute, for low number density materials, such as found by dissolving a chromophore in a polymer to create a composite material or covalently attaching that chromophore to a polymer backbone. But you would also note that in addition to considering these low number density materials which account for this level of improvement, since 2014 we've had a dramatic improvement in electro-optic activity by going to high number density materials. And this involves a dramatic complication of the system and an entirely expanded theoretical treatment, which we'll describe later on in this talk. I'd like to turn our attention to the fundamental equation for devices and the fundamental equation for device figure of merit. Of course, this equation will change with different types of device structures, and so what I show you here is the equation for the Mach-Zehnder interferometer that we've introduced you to. And the critical parameter is the voltage length parameter. And when you think about technology, you'd like the devices to be as small as possible, and you'd like to have them require as little voltage to operate as possible. And in particular, you'd like to have the operational voltages be digital voltage levels of a few volts, or otherwise you'd have to introduce amplifiers, which would be very expensive, take up a lot of space, and would limit the bandwidth that you can achieve with devices. Now, you would note that this critical figure of merit for devices relates inversely to the electro-optic activity. So the bigger electro-optic activity, the smaller V pi L. And it also relates to the separation between the drive electrodes. And we might also note in passing that electro-optic activity induced by pulling also relates to the separation of the pulling electrodes, which are one and the same here. Now, I'd like to move on to this figure, which talks about the three fundamental carriers of information, electrons, photons, and plasmons, and would note that electronics permit very small devices, but the operating speed or bandwidth is not very good. And that's the reason is because electrons have strong electron-electron interactions. And so there are resistive losses in terms of transmitting electrons through metal wires. And photons, on the other hand, have essentially no interactions, and so very high speeds can be achieved, but until recently, critical dimensions for photon devices were limited to about 1 micron. Plasmonics permit both high speed and short size, but the losses for plasmonic propagation are very large, and the only way they're going to be feasible is if you can go to very short devices. Also, each of these devices by themselves, each of these fundamental carriers by themselves are not active elements. You need to have some type of device technology that can actually interconvert between these various domains and that can, for example, take information encoded on electrons and transmit it to information coded on photons. Now, this is the critical slide for improvement in performance realized in the last few years here at UW. We take as our reference material lithium niobate. And lithium niobate is the cathode ray tube of electro-optics. It was used in every critical telecom demonstration, including the transatlantic cable. So any telecom engineer immediately recognizes this and will choose this material instinctively because it's a safe choice. I might note that if you look at a forthcoming issue of Applied Physics Reviews, a full issue is devoted to lithium niobate. So everyone sort of takes this as the reference point for comparing your technology to this technology. There is a fundamental problem. A lithium niobate device is 10 centimeters long with a drive voltage of 4 to 5 volts. And so its voltage length parameter is terrible and could never be used for chip scale technology. And indeed, our current best devices represent about a factor of a 10,000 improvement over lithium niobate. And I'm sure some of you will immediately say, well, that's an unfair comparison. You should be comparing against the very best competitive electro-optic technology, for example, that being pursued at Intel, UC Berkeley, Stanford, et cetera. And that best technology is carrier injection silicon modulator devices. And the voltage link parameter for that technology is 360. So it's about an order of magnitude worse than our devices, which have a VPI volts per micron, a voltage link parameter of 40 volts per micron. Footprint is another critical issue, and as we've just noted, lithium niobate has an enormous footprint, so the factor of improvement is about 10 to the 8th. Energy efficiency is very important, particularly if you're going to do dense integration, and we get about a factor of 10 to the 7th improvement here. Bandwidth is another critical issue, and terahertz our hybrid technologies can operate to bandwidth in the terahertz region, which is a dramatic improvement over lithium niobate, even much greater than this factor of 10 shown here. Insertion loss is the one, by the way, I might note that that silicon injection modulator has terrible bandwidth, worse than lithium niobate. The parameter that lithium niobate excels on is insertion loss, because it's a very transparent material. But I would note that insertion loss depends on device length, which in turn depends upon electro-optic activity. Hence, as electro-optic activity is improved in organic electro-optic hybrid devices, this value will drop down. Now, all the technologies shown here are Pockle set effect modulation. That means when you apply the voltage, the only thing you do is produce a phase change. Electroabsorptive modulators and silicon injection depletion modulators involve both a phase change and absorption. That produces signal distortion. So their signal linearity is very poor. That is, the spur-free dynamic range for analog signals and bit error rate for digital signals is barely usable, but is excellent for all of these Pockle effects. And indeed, we would note for our current devices, we have bit error rates less than 10 to the minus 9th. And the decision point for a bit error rate is 5 times 10 to the minus 3rd. So we're orders of magnitude, which means we're not going to be producing errors in digital signal handling. All of these technologies have passed telecordia standards, and any photonic technology has no significant crosstalk. And so unlike electronic elements, which can interfere with each other, you can put photonic elements right next to each other with no problems. Now, sadly, this wonderful performance, which you might say, this is shocking, why aren't we using it right now, is likely going to require further improvement if we are really going to be successful with chip-scale integration. So we're not competing against lithium niobate or any other electro-optic technology at this point. We're competing against realizing the Holy Grail, or we're pursuing realizing the Holy Grail of chip-scale integration of electronics, photonics, plasmonics, and other technologies. Now, I'd like to just briefly acquaint you with device architectures and also some of the types of device structures that we pursued. Initially, we pursued silicon organic hybrid device architecture such as shown here. So what we do is we take a silicon waveguide, which is already with dimensions on the order of a few hundred nanometers rather than micron dimensions of a lithium niobate modulator. And we cut slots in this. And these slots can be as small as around roughly 25 nanometers. You fill the slots with organic electro-optic materials. I show you the polling fields and denoted in black, and the RF drive fields. And so you, in this configuration, produce a push-pull modulator. This device is has a V pi that's roughly a factor of 10 worse than V pi L that's roughly a factor of 10 worse than our best devices. But the point I would particularly like you to note is that this structure concentrates both the optical field and the RF electric field in these nanometer slot regions. And that leads to a dramatic enhancement of the optical nonlinearity. Remember, optical nonlinearity is going to be determined by the strength of the electric field you apply and the ease at which your charge distribution is perturbed. Now, this particular device we've already seen can be used to transduce electrical signals onto optical signals and amplitude modulation. In telecom, very sophisticated modulation protocols are implemented. And the fundamental architecture for implementing these, where you can actually utilize different phase and different amplitudes, is represented by this in-phase quadrature modulator configuration, which consists of coupling two Mach-Zehnder modulators in parallel. And the current best device architectures that we're using are plasmonic-organic hybrid modulators. And what you have here is light being brought in a silicon waveguide being converted into surface plasma and polaritons through this region of a metal insulator metal device where the insulator is organic electro-optic material, and then back converted to a photon. And the information or signal is encoded by applying a voltage and perturbing the phase of the propagating plasma, surface plasma and polariton. Again, you note that you're concentrating both optical and electrical fields in these low-frequency electrical fields in these nanometer slots. When I say low frequency, you realize this ranges from DC up to about 30 terahertz, so it's a pretty broad range. But of course, optical fields are much higher frequency. Now, the devices I've talked about thus far are called strip-line devices, and light makes a single pass through the device. There are also resonant devices, such as these ring microresonators, where light's going to pass multiple times through the modulated region. And that's going to enhance your modulation effect. So it's a way to drop the required voltage. It's also a way to get a long path length with a very compact device. And indeed, we worked back in 2008 with Boeing on these devices, including applications such as this 4x4 rig configurable add-drop multiplexer, which basically allows you with voltage control to take any input signal here and switch it to any output signal. So it's a method of managing the transport of information. Now, we no longer pursue this, even though Boeing continues with this work, because the plasmonic modulator gives us the same V pi's without the engineering complications. And of course, if you run through a resonant device, not only do you achieve amplification, you also limit your bandwidth, because the lifetime of the photons in this device define the bandwidth. Now, we carried out demonstrations of medium-range telecommunication using our devices, implementing all the advanced modulation formats. This is done basically in Switzerland, courtesy of our ETH collaborators. And we've done this with record-setting performance for telecom in every case. We've also implemented large-scale integration where you're putting a lot of modulators on a single chip. Now, one of the issues with doing this is obtaining uniform polling for each of these modulator devices. And this shows you one example of a parallel polling configuration that's worked very successfully in doing this. In fact, we get a 100% yield with very little variation in performance from modulator to modulator. This shows the connection of electrical inputs for the actual drive of a modulator in this multi-modulator configuration. Now, we can also make a variety of sensors, and this shows you an antenna sensor function, which is a favorite of mine that's coming out in nano letters, because this device produces direct conversion of wireless signals to fiber optic signals. This is done routinely in telecommunication, but now the way you do this is you convert this electromagnetic radiation to an electrical signal, which requires introduction of amplifiers, and then you convert that electrical signal to an optical signal. This is a dirt cheap device that does it with terahertz bandwidth and a factor of 35,000 enhancement of that incoming wireless signal. You can see the footprint is very, very small. And I would note that you can also use this very simple device configuration that's easily manufactured and quite inexpensive as a terahertz sensor. Now, there are a variety of more sophisticated devices that you can produce with the basic architectures and devices that I've talked about. This is an example of a frequency comb source for terabit communication. You see here we've generated a number of wavelengths, and you can encode information on each of these wavelengths, and that's called wavelength division multiplexing, which I'm sure you've heard about. It's widely used in telecom. We can also produce a difference frequency generator, where we can generate RF signals from a few gigahertz up through the terahertz region. Now, there are many other applications, including optical gyros. Because we're running a little late on time, I'm going to skip through those and turn to an overview of the optimization of materials using multiscale methods. And there are two components to this. The first component is using time-dependent hybrid density functional theory for calculating linear and nonlinear optical properties of our materials, and using that theory to guide the next chromophores to be produced. We also need to develop coarse-grained, monocolor, and molecular dynamic statistical mechanical methods to simulate polling-induced order and dynamics. And we note that electro-optic materials exhibit both centrosymmetric, even, and acentric, odd order parameters, and that the ratio of these define lattice symmetry. So this is a great system that experimental data allows us to do a really good test on theory. And this is some of the publications that have described various theoretical methods. Now, I'd like to break our theoretical consideration into two time periods. The first deals with theory applied to low number density materials. So this is taking a chromophore like this and dissolving in a common polymer like polymethyl methacrylate. And initially, everyone assumed that these would behave as independent particles and that the electro-optic activity would increase in a linear manner with number density because the acentric order parameter was independent of number density. Well, as you see experimentally, this is what everybody saw. So my grant monitors at the federal agencies asked me to explain this, and fortunately we have Bruce and his students as well as myself involved. And so what we're able to do is model this by treating this chromophore as a single ellipsoid, so it's a coarse-grained approximation to the chromophore, and we're going to take into account the fact that this has a significant dipole moment. So the reason that this curve rolls over is dipole-dipole interactions between chromophores tend to drive centrosymmetric organization. And the exact nature of the curve is defined by the shape of the chromophore as well as the dipole dipole interactions. And of course, shape is defined not only by this pi electron system, but by whatever you hang off these various regions. And so theory says if you can make this into a spherical shaped chromophore, you get dramatically improved electro-optic activity. And this led to our, very quickly to a 2000 Science paper, which received about 1,000 science, 1,000 citations and also a great deal of news coverage. But if you look at this, before I go to the next slide, you'd naturally assume this is just going to keep going down. You're going to get one maximum here. Up here, you're going to be centrosymmetric organization. In fact, if you take this chromophore, it's going to crystallize. If you take it and just grow a crystal in the absence of a Pauling field, it's going to crystallize in a centrosymmetric configuration. But you'd be wrong, and as shown both by Andreas Tillich theoretically and shown theoretically by Alex Jen and my group and others, that you get this second minimum, the second maximum at high number density. So you get one number density down here, you get the second maximum in the electro-optic activity at higher number density. And you also get two maxima in the acentric order parameter. Now, if you go to high number density, life becomes much more complicated. First of all, chromophore shape becomes more important because the chromophores are more packed in more tightly. So Andreas found that the single ellipsoid was no longer a good representation of the chromophore. And in fact, he had to use two ellipsoids or a level of detail of 2 to get quantitative simulation. The other thing that he showed by considering modification of the chromophore to change its shape was that yes, you could continue to increase acentric order as you increase the radius of your protecting group, but note you go through a maximum in the plot of electro-optic activity, or the product of number density and order parameter. Because as you're increasing this, you're also dropping the chromophore number density. So these two terms, number density and acentric order, start to compete, and you end up with a maximum. So it tells you you don't simply want to blindly modify chromophores. Now I'd like to discuss 3 critically important improvements that Bruce Robinson and his group have made in statistical mechanics coarse-grained method. Coarse-grained methods, of course, can be fully atomistic. Statistical mechanical simulation can be fully atomistic, but really that takes too long in terms of time. So coarse graining has become very popular. It's normally done by using a sphere to represent a collection of atoms. And as Bruce and his students have shown, that's a very bad approximation. In fact, they've done a very nice job of simulating the dielectric permittivity of dipolar liquids ranging from water to acetonitrile to other dipolar materials by using shaped objects for the united atom approximation. Another thing we just noted that Andreas did was to use different levels of detail as required. For example, this works fine, a level of detail of 1, if you're talking about low number density materials. But as you go to higher number density materials, you have to use a higher level of detail. The next thing that Andreas did that was really nice is he really solved the method of avoiding calculations hanging up in pseudo-minima. Remember, we're simulating the behavior in condensed phases. And so these chromophores, a trajectory run may hang up in a non-equilibrium configuration that is characterized by a low acentric order. So what he does is really sort of model the process of going from solution or from the gas phase to a solid material, as for example would occur in crystallization, using this adiabatic volume adjustment method in simulation. And this has led to significantly improved simulation, For example, here using the adiabatic volume adjustment method, he simulates the experimentally observed polling value, while more traditional approaches underestimates the electro-optic activity obtained by polling. Another nice feature of this work is he's been able to gain insights into why some systems experimentally have problems in aggregating. So what have we learned from theory? Well, we've learned that we can impact properties such as electro-optic activity by modifying chromophores, for example, to change their fundamental shape. But my students and Bruce's students have also shown that and Alex Jins and his students have shown that you can modify chromophores with groups that undergo long-range intermolecular interactions like coumarins or benzene perfluorobenzene materials, where these dipolar and quadrupolar interactions promote long-range cooperativity that impacts the lattice symmetry that the chromophore senses. And as shown by this theoretical slide, where this is the acentric order parameter, this is the effective polling field, as you go from a three-dimensional lattice felt by the chromophore to a two-dimensional lattice, you double the electro-optic activity or the acentric order parameter in the electro-optic activity. And Stephanie Benet and Alex and his students have shown this to be experimentally observed. We can also modify chromophores to incorporate groups for lattice hardening. For example, we may want to increase the thermal and photochemical stability of a material by making the lattice more dense and elevating the glass transition temperature, and this can be done by these types of cross-linking reactions. Theory has inspired a number of new materials introduced by Stephanie Benet and Phil Sullivan, and new processing techniques such as laser-assisted electric field polling, which can also be used to control lattice symmetry surrounding a chromophore. Well, lattice hardening can be very important, as we'll show in just a second, and these are the historical methods of lattice hardening that have been used. And the good news is they allow us to elevate the glass transition temperature up to 200 degrees C and above. And that's been very nice for surpassing Telcordia standards. Now, a number of new material characterization and processing methodologies have been introduced. And this is where Phil Reed and René Auvernay and a number of people come into play. And these techniques can provide dramatically new information on partially ordered materials. For example, variable angle spectroscopic ellipsometry can give you the order parameters of both chromophores and groups like the coumarin groups, but they can also give you the relative orientation of the groups. And in the case of her materials, these are oriented roughly at 90 degrees with respect to each other, which is what you see in this theoretically generated cartoon. René Auvernay and Stephanie and others have used nanoprobe technique to measure dynamics, phase transitions, and thermodynamic properties. This shows you the variation of what is the effective entropy of a system as it goes into a two-dimensional phase. And a two-dimensional phase is also predicted by the ratio of centric to acentric order parameters, as we noted earlier. And the maximum polling efficiency, which is observed experimentally, corresponds to this greatest reduction in entropy, or this best ordered two-dimensional lattice. Now, we're coming to the end, and there are some problems I should note, or as Alvin would say, insurmountable opportunities. And I'd also conclude with some future prognosis. The first problem is, even though we did very well, we probably need to improve things by about a factor of 4 to 8, because of the crucial accompanying improvement in bandwidth, energy efficiency, and insertion loss, and also into parameters such as bit error rates, because all these depend upon length of device and upon drive voltage, which depends upon electro-optic activity. Now this could be accomplished in any of these ways by improving the beta of the chromophore, the product of number density and order parameter reduction of conductance that occurs at polling conditions, improvement of device architectures, interface control, use of novel photonic crystal and metamaterials architectures, and also by dealing with our inorganic materials, for example, finding new plasmonic materials, using nanostructured plasmonic materials, reducing plasmonic heating and optical loss. Now, we know from our theoretical work and synthetic work, this is not a trivial task to accomplish these. Now, we would note that all these problems and more, signal linearity, are associated with the other non-Pockels technologies. The other problem that we need to be aware of, which isn't really a problem yet, but it could be, is that these nanometer dimensions of our plasmonic-organic and silicon-organic hybrid devices lead to dramatic concentration of fields. And these high fields could conceivably create photostability problems. This hasn't been a problem yet, but it may be well that we actually think about lattice hardening to deal with this if it becomes a problem. Plasmonic heating is, again, a potential problem. Now, we note that this hasn't been a problem yet, and it probably isn't a showstopper, but we need to be aware of it. The other final problem I would call to your attention is that density functional theory may not be appropriate for high number density materials, where the chromophores are coming so close together that you can have pi-pi or excitonic interactions. And no one knows the effect of these types of interactions upon material electro-optic activity. So this is an area that clearly needs theoretical attention, and to this point in time, it's largely an untrodden area. Why I conclude by acknowledging our current funding. Our NSF, we've just received our third creativity award from NSF. And I show you some, because of intellectual property concerns, I haven't talked about unpublished work. I show you in these next two, in this slide and the next slide, literature associated with devices that I just talked about, and also literature associated with theory and materials. And with that, I thank you for your attention.